In the previous units, we found the enthalpy and temperature a gas reaches when it's brought to rest. But what about the peak pressure the flow reaches? This is going to be very important in calculating vehicle drag and structural loads. In order to compute the pressure where the flow is stagnated, we need to make an extra assumption about how the flow is brought to rest. We assume that the process is reversible as well as adiabatic, making it isentropic. This means we can make use of the isentropic flow relations. If you recall, the first isentropic flow relation we derived was that the pressure ratio across an isentropic process was equal to the temperature ratio to the power of gamma over gamma minus 1. Let's make state 2 in this relation the stagnated flow state, and state 1 the state when the flow is at a Mach number of m. If we use the expression for T0 over T from the last unit, we see that the stagnation to static pressure ratio is given by 1 plus gamma minus 1 over 2 times the Mach number squared, all to the power of gamma over gamma minus 1. This is the factor by which the pressure would be multiplied if the flow at Mach number m was brought to rest by an isentropic process. Let's make use of this equation to solve an example problem. Earlier in the course we said that we'd be able to properly compute the pressure encountered by the front of a Bugatti Veyron when it stagnates the airflow moving over it, once we knew a little bit more about compressible flow theory. The reason we needed to apply some compressible flow theory was that the top speed of this car is fast enough that compressible effects become important. So now our knowledge should be up to the stage where we can do this calculation. So let's go ahead and do it. Okay, so the first thing we need to do is to calculate the Mach number m, which is equal to the speed of the vehicle divided by the sound speed a, and we know that the sound speed is the square root of gamma RT. Okay, so in meters per second, the speed of the vehicle is 120. Gamma for air is 1.4. The gas constant is 287, and our temperature of the atmosphere is 298 Kelvin. Okay, if we go ahead and plug this into a calculator, we're going to find that our Mach number is 0.35. Now we can use the expression that we just derived for the stagnation pressure P0. It's going to be equal to the static pressure multiplied by 1 plus gamma minus 1 over 2 times the Mach number squared to the power of gamma over gamma minus 1. Okay, so the atmospheric pressure, which is our static pressure in this case, is 101 kPa. And then we've got our 1 plus gamma minus 1, which is 1.4 minus 1 in this case, over 2 times our Mach number 0.35 squared. And then this is to the power of 1.4 divided by 1.4 minus 1. Plugging this into our calculator once again, we're going to find that the stagnation pressure against the nose of the Veyron is 110 kilopascals. Okay, so it's only about 9 kPa higher than atmospheric pressure, but there was a bit of a compressibility effect in this number. The difference between atmospheric pressure and this stagnation pressure is about 5% greater than what you would get if you used incompressible flow theory. This is only a fairly minor difference, but it would be important in an engineering calculation, and this really tells us that we're on the borderline Mach number where compressibility effects start to become important. We now know how to calculate the stagnation enthalpy, temperature, and pressure. But what about the other stagnation properties? We can find the ratio of the stagnation's sound speed, A0, to its present value, A, just by expressing both sound speeds as the square root of gamma R times the relevant temperature. The root gamma R's cancel, and so all we're left with is the square root of the ratio of the stagnation to static temperature. Using our expression for T0 over T once again from the last unit, we found that A0 over A is equal to the square root of 1 plus gamma minus 1 over 2 times the Mach number squared. To find the ratio of the stagnation density to its value at a Mach number of m, we make use of the ideal gas law to express both of the densities in terms of temperature and pressure. Cancelling out the gas constants, we see that the density ratio is equal to the pressure ratio divided by the temperature ratio. And we already obtained expressions for both of these in terms of the Mach number, and we make use of those here. After simplifying the power, we find that the stagnation density ratio is given by that same combination again, 1 plus gamma minus 1 over 2 times the Mach number squared, this time to the power of 1 over gamma minus 1. We can also invert these expressions for stagnation quantities to examine the situation where we have a high pressure gas stored stagnant in a reservoir, which is then allowed to expand and accelerate through a nozzle. This plot shows how each quantity drops from its stagnation value as it's accelerated to the Mach number on the x-axis. We see that the pressure in light blue drops most rapidly, followed by the density in red and the temperature in green. Finally, the sound speed drops the least quickly. The state of the fluid when the Mach number is 1 is known as the critical state. We'll find out in the next subsection that the critical state is very important in the analysis of compressible flows. The relations between the sonic state, which is denoted with a star, and the stagnation state can be found simply by substituting a Mach number of 1 in our relations for the stagnation properties. For gamma equals 1.4, which is the value for any diatomic gas, such as the nitrogen and oxygen in air, we find that the critical pressure is 53% of the stagnation pressure. This implies that air only needs to be stored at about double atmospheric pressure before it can reach the speed of sound when venting into the atmosphere. The critical temperature is 83% of the stagnation temperature, and this can easily be used to compute the critical velocity, which is equal to the critical sound speed, seen as how the flow Mach number is 1. In the next section, we're going to make use of the critical state and the stagnation properties in the analysis of compressible flow through nozzles, such as the one required to extract thrust from the hot exhaust products exiting from a scramjet combustor.